Apples, onions, tea leaves. You consume them regularly, and when you do, you ingest a flavonoid called quercetin. For decades, nutritionists have understood it primarily as a reliable dietary antioxidant that helps neutralize everyday cellular wear and tear. In a high-dose laboratory environment, isolated quercetin behaves as an aggressive biological agent, actively seeking out and dismantling malignant cells. Modern oncology frequently relies on single-target drugs, medications designed to block one specific pathway. Tumors, however, are highly adaptable survival systems. Block one route, and the cancer simply routes around the drug to stay alive. Quercetin behaves differently. It functions as a biological multi-tool, simultaneously attacking several of the tumor's critical life support systems at once. To understand how to deploy this tool effectively, we have to map the specific cellular machinery it targets, starting with the massive energy demands of a growing tumor. Cancer cells undergo metabolic reprogramming. They abandon normal cellular respiration, switching to a process called glycolysis. This allows them to gorge on vast amounts of glucose, using that sugar to rapidly build new biomass and multiply. Quercetin attacks this exact pipeline. It blocks GLUT1 transporters, the literal gates that let sugar into the cell, and inhibits a key digestive enzyme called PKM2. Quercetin effectively slams those gates shut, cutting off the food supply. Tumors also require a heavy supply of iron to fuel their rapid expansion. Quercetin acts as an iron chelator, meaning it binds to excess iron in the body, stealing it away before the cancer cells can absorb it. This table highlights how other natural compounds operate, showing the molecular targets for garlic-derived bioactives like allicin and DATs. While those target inflammatory pathways like NF-kappa B and MAPK, quercetin specializes in metabolic starvation. By simultaneously restricting both glucose and iron, the tumor's ability to replicate is severely compromised, leaving it highly vulnerable to a deeper genetic dismantling. A healthy cell is programmed to self-destruct if it becomes damaged. Tumors survive by mutating a gene called p53 and producing heat shock proteins to ignore those death signals, essentially giving themselves an invincibility shield against the immune system. Quercetin directly intervenes here. It downregulates the mutated p53 genes and inhibits the production of those heat shock proteins. It strips away the tumor's defensive shielding. This text excerpt outlines how quercetin works alongside standard oncologic therapeutics. It isn't meant to replace conventional treatments. In lab models, adding quercetin actually potentiates the effects of chemotherapy drugs like cisplatin, making them up to 30 times more cytotoxic to the cancer cells. This is due to a biphasic switch. At low doses, quercetin is an antioxidant. At high doses, it becomes a pro-oxidant, triggering cellular collapse, forcing the cancer into apoptosis or programmed cell death, and autophagy, where the cell literally eats itself. Hitting the metabolic supply lines, stripping the genetic defenses, and amplifying standard chemotherapy makes this flavonoid a highly compelling candidate for integrated oncology. There is a massive biological hurdle: absorption. Quercetin has famously low bioavailability. If you take it orally, gut bacteria break it down and your liver clears it out rapidly, making it incredibly difficult to reach those high therapeutic concentrations in the bloodstream. This flow diagram illustrates the rigorous tracking required to verify if a repurposed drug or supplement actually works in humans. Researchers have to design complex, multi-wave studies to track patient outcomes over months of real-world use. This infographic displays the distribution of common cancer types in such cohorts. To understand a compound's broad efficacy, researchers monitor its effects across a wide spectrum of malignancies, with prostate and breast cancer often making up the largest groups. This data table lists prior and concurrent treatments. Proving a supplement's exact benefit requires accounting for this noise, filtering out the effects of prior surgeries, radiation, and immunotherapies to see what the compound is actually doing. To solve the absorption problem, researchers are turning to nanoengineering. By wrapping quercetin in liposomal capsules, or PEG coatings, they can shield the molecule from the liver and gut, increasing its delivery to target tissues by up to 5-fold. Looking at this infographic on adherence and safety outcomes, we see that the success of any future protocol relies on keeping dosing strict and consistent, maintaining the exact therapeutic pressure needed to keep the tumor weak. Whether delivered through microcapsules or directly via IV, nanotechnology allows these compounds to act as a Trojan horse, bypassing the biological wall entirely to reach the exact blood concentrations required. Integrating these multi-targeted natural properties with synthetic delivery systems creates a pathway to bypass previous biological limits and deploy quercetin effectively in integrated oncology.